Hi there. In this video, we will cover how to prepare geometry files for use in the orbital stack application. Ensuring your geometry files are correctly prepared is one of the first and most critical steps to make sure your simulations return the best possible results. First, let's cover some principal requirements that apply to all geometry used with orbital stack. All geometry files must be in STL format. STLs can be uploaded as binary or ASCII format. CAD programs such as SketchUp, Revit, AutoCAD, and Rhinoceros all support exporting files in STL format, as well as many others. Your geometry should be exported in a full 1:1 scale with meters, with true north oriented in the positive y direction. And finally, geometry files should be limited to 20 megabytes in size for AI simulations, or 50 megabytes in size for CFD simulations. Now, let's take a look at what is typically included in our project geometry. The base geometry of each configuration is uploaded as 3 distinct parts, each with a separate STL file. The ground, the context or surrounds, and the study. The ground model should have minimal details and simplified topography. Only include essential grading, otherwise it can be created as a flat plane. Ensure the ground does not contain any large holes, seams, or disconnected surfaces. The ground should also extend past the extents of all context buildings. The context model includes all surrounding buildings within a 250 to 300 meter radius of the project site. Ensure that all context buildings fully penetrate the ground surface, as buildings floating above the ground will have a negative impact on your simulation results. This can be done by extruding the bottom of any building geometry downward. The study model contains all elements that form the basis of the proposed development or existing structure. This model should lie near the origin of the project with coordinates 0, 0, 0, and the ground study intersection point should have a z-coordinate of 0 meters. All buildings should be free of any interior elements and be configured as a simple block massing. Exterior cladding elements or details smaller than 0.5 meters should not be included. The project should also not include small pedestrian level elements like railings, signage, seating, or thin columns. For an in-depth list of the types of details you should or should not include, please refer to our Preparing Geometry page on our help site. In addition to your main 3 geometry files, presentation planes are also included at all locations where results are to be visualized. These areas can include the ground surface surrounding the study, outdoor amenity spaces, balconies, patios, or rooftops. Presentation planes must be raised 1.5 meters above the surfaces they are capturing and should be limited to areas wider than 3 meters. Presentation planes cannot be volumetric. They must be 2-dimensional and planar. They must also not intersect or collide with the ground plane. Volumetric or intersecting presentation planes will have negative impacts on the simulation results. A simple and effective way to create your presentation planes is to select the surfaces of interest on your study, duplicate them, and raise them by 1.5 meters. The ground level presentation plane can be created in a similar fashion, or by making a smaller plane that encompasses only the area around the study and raising it. Once all presentation planes are created, export them as their own STL file. Presentation planes can be uploaded together as a single STL or in subgroups based on the type of area they represent. Users can also upload optional geometry elements as overlays for visualizing streets, sidewalks, and objects that do not influence the simulation. Since presentation surfaces are raised 1.5 meters, raise overlays to 1.7 meters above grade to ensure visibility above results. Now that we've covered the essentials, let's look at a sample project with some common geometry issues and show how to prepare our project for simulation in the orbital stack application. In this project, we have 2 study buildings shown in pink. The context, shown in gray, includes the surrounding structures, such as buildings and an elevated roadway. Let's check the model units. This model was created in a 1:1 scale with feet. All geometry used with orbital stack needs to be in meters, so let's convert the units appropriately. Next, let's turn on the origin plane and confirm the geometry's position in 3D space. We can see that our project is elevated above the origin plane. Let's translate the whole project downward so that our project ground matches that of the origin plane. This model also includes some small details around the base of the study building, some benches, and a nearby fire hydrant. These elements are too fine and should not be included in the simulation, so let's delete them. We can see that the other buildings and structures in our model are modeled with an appropriate level of detail. Buildings are simple block massings and have no internal elements or fine cladding details. Zooming into the base of our study buildings, we can see that they appropriately lie near the origin. There does, however, seem to be a couple holes in the mesh of one of our podiums. Gaps or holes in our structures will have a negative impact on our simulation results, so let's patch these up. Now let's have a look at the ground surface. Here we can see that the ground surface does not extend far enough to capture all of the context buildings. The ground plane should extend past the extents of all context models. So let's increase the size of the ground plane. With our ground plane now appropriately sized, let's check to see if all of our buildings fully penetrate the ground surface. Looking from underneath the model, we can see which elements are showing through the ground. It looks like two of our context buildings are floating above the ground, which can cause issues with our simulation results. So let's fix them. The easiest way to correct this issue is to select and extrude the bottom of these buildings downward to penetrate the ground. Let's turn the ground model back on, and now we can see that the buildings fully pass through the ground surface. Let's move on to presentation planes. In this project, we can see we have included presentation planes at ground level surrounding the study area and on various levels of the study building's podiums. There seems to be an issue with our ground level presentation plane. In this case, it's coincident with the ground plane and needs to be elevated above the ground by 1.5 meters. We can do this by simply selecting the plane and moving it upward. Now, the presentation plane lies at the correct elevation of 1.5 meters above grade. Let's have a look at some of the presentation planes on our study buildings. On this first building, we can see that the presentation planes are raised appropriately at each level. How about the second building? On this building, we can see that 4 of our presentation planes are not planar, but rather volumetric. Volumetric presentation planes will have a negative impact on our results. So let's recreate them and ensure that they are not volumetric, but rather two-dimensional and planar. We can recreate these surfaces by selecting the surfaces they are above, duplicating them, and translating them upward 1.5 meters. With that, our project geometry is now simulation ready. All that is left to do is to export the parts of our project into appropriate STLs, a separate file for the study, the ground, the context, and the presentation planes. For more information on how to create a project and upload your geometry files to a new scenario, please refer to our help site, where you can check out some of our instructional articles or view another video tutorial. Thanks for watching.